Good afternoon, distinguished colleagues and guests. It's March 23rd, 2022, 12 noon Moscow time. And we're beginning the panel session for the defense of the thesis by Maksim Dolgopolik. The thesis is submitted for the academic degree of Doctor of Sciences in Physics and Mathematics. The specialization is 111, real, complex, and functional analysis. The topic of the thesis is constructive non-smooth analysis and its applications to optimization, calculus of variations, and control theory. Under the order issued by the Academic Secretary of St. Petersburg State University, Alexander Knyatov, as of November 23rd, 2021, number 11303/1, I, Lyudmila Polikova, Doctor of Sciences in Physics and Mathematics, Professor, acting head of the Department of Mathematical Modeling of Control Systems of St. Petersburg State University, was appointed the chairwoman of the board. The order also approved the candidacies of the members of the board, and let me introduce them. The following members of the board are working remotely, namely Vladimir Yerokhin, Doctor of Sciences in Physics and Mathematics, Professor, Senior Researcher at the Mazhaysky Military Space Academy of the Ministry of Defense of the Russian Federation. Alexei Matveyev, Doctor of Sciences in Physics and Mathematics, Professor. Oh, I forgot to ask Vladimir. Vladimir, do you hear us? Yes, I do. Okay, thank you. Alexei Matveyev, Doctor of Sciences in Physics and Mathematics, Professor, Head of the Department of Theoretical Cybernetics of St. Petersburg State University. Alexei, do you see and hear us? Yes? Yes, thank you. Okay, thank you. Maksim Balashov, Doctor of Sciences in Physics and Mathematics, Associate Professor, Leading Researcher at the Institute of Control Sciences, named after Trapeznikov of the Russian Academy of Sciences. Maksim, do you see and hear us? Yes? Alexander Strikolovsky, Doctor of Sciences in Physics and Mathematics, Professor, Honorary Scientist of the Russian Federation, Head of the Department and Leading Researcher at the Matrosov Institute for System Dynamics and Control Theory of the Siberian branch of the Russian Academy of Sciences. Alexander, do you see and hear us? Yes? Both. Thank you. Fyodor Stanyakin, Doctor of Sciences in Physics and Mathematics, Associate Professor at the Department of Algebra and Functional Analysis at the Vernadsky Crimean Federal University. Fyodor, do you see and hear us? Fyodor? Yes? Yes, I see and hear you. Vera Roshina, Doctor of Sciences in Physics and Mathematics, Professor at the University of New South Wales in Australia. Vera, do you see and hear us? Yes, I do. Thank you. And our candidate for the degree today is Maksim Vladimirovich Dolgopolik. Hello. And also remotely we have the academic consultant of Mr. Dolgopolik, Alexander Fratkov, Doctor of Technical Sciences, Professor, Head of the Complex Systems Control Laboratory at the Institute of Mechanical Engineering Problems of the Russian Academy of Sciences. So, Alexander, yes, I'm here with you. Okay, thank you. I would like to inform you that the panel session of the Dissertation Board is being recorded and broadcast on the St. Petersburg State University website, and it is also interpreted from Russian into English, or in case it's needed, from English into Russian. Currently, we have an email address posted on the page with live broadcast of our board session, and all listeners can submit their questions to the applicant online, or maybe they can voice their opinions regarding the content of the thesis or the presentation of the applicant for the degree, or maybe the scientific discussion, and thus they can participate in the discussion. These questions will be forwarded to me by our technical service, and I will read them out during the discussion. The questions must be directly related to the speech and presentation of the applicant and to the content of the thesis, and don't forget to state your name and position if you submit a question. The questions that have nothing to do with the scientific discussion and the discussion of the dissertation or anonymous questions will not be voiced. Under the order on the procedure of granting academic degrees at St. Petersburg State University, approved by the local regulatory acts of St. Petersburg State University, herein the order. The session of the board is valid, providing 2/3 of the appointed board members are present, and the total number is not to be fewer than 4 people. Our board consists of 7 people. Everyone is with us today, including 7 members of the board, 6 members of the board who joined us remotely. We have a multimedia connection with all of them, therefore we have the quorum. And I kindly ask the member of... I beg your pardon. I kindly ask the member of the Department of Dissertation Board Support to fill out the attendance list. And our agenda for today is as follows. Overall, we have 3 hours, no more than 3 hours for the board session. So first, we're going to listen to the chairman's short, brief presentation about the documents submitted by the candidate for the degree and their conformity with the requirements, followed by chairman's replies to questions, if any. Second, the candidate's brief presentation providing an overview and the findings of the research. "20 minutes. Then questions to the candidate regarding the presentation, no more than 2 minutes per question. The candidate's replies to the questions. Then reports on the thesis. The board members will be taking the floor in turns to provide their reviews and questions. 10 minutes each. Then the chairman's report on the thesis. Also 10 minutes. Then the applicant's comments about the report on the thesis and replies to the questions voiced. Afterwards, we're going to have an open discussion, speeches by those present at the defense, with a brief presentation of their positions or questions or suggestions to the applicant for the degree on the topic of the research, 2 minutes each. And don't forget to state your full name, academic rank, position, and place of work in the registration list, and don't forget to introduce yourself before I give you the floor. Then the chairman will ask the questions submitted during the broadcast via our website. And I would like to draw your attention to the following fact. Written questions that will take more than 2 minutes to read out will not be voiced. Then the candidates' replies to the questions, followed by the presentation of the candidate's academic consultant. And afterwards, we're going to have a 5-minute discussion before the open balloting on conferring or non-conferring the academic degree. The discussion of the results of the defense is not broadcast. Afterwards, we're going to have an open balloting. We're going to count the votes and record the results in the protocol. Finally, we're going to make a decision on whether to confer the academic degree or not. And the candidate, I'll listen to the candidate's closing speech. 2 minutes will be given for that. Distinguished colleagues, any objections or questions on this agenda? No, none. No objections. Okay, so first of all, I kindly ask you to switch off the sound on your mobile phones. And those members of the board who are working remotely, I kindly ask you to switch off your microphones in order to improve the quality of our connection. But please don't forget to turn them on when I give you the floor. Thank you. Well then, let's begin. A thesis by Maksim Dolgopolik for the academic degree of Candidate of Sciences in for the academic degree of Doctor of Sciences in Physics and Mathematics, specialization 111 Real Complex and Functional Analysis, is titled The Dynamics. Is titled Constructive Nonsmooth Analysis and its Applications to Optimization, Calculus of Variations, and Control Theory. The thesis was approved for the defense by the order of the Academic Secretary of St. Petersburg State University as of November 1st, 2021, number 10660/1. Maksim Dolgopolik has prepared his thesis at the Institute for Mechanical Engineering Problems of the Russian Academy of Sciences, where he works as a senior researcher, and his academic consultant is Alexander Fredkov. I have already introduced him. 29 published works describe the research findings, and 28 articles are published in journals indexed in Web of Science and Scopus. And there's one article published in a journal recommended by the Ministry of Education and Science of the Russian Federation. All the documents submitted by the candidate for the degree comply with the requirements of St. Petersburg State University and are kept in the certification file of the applicant for the degree, and the curator of the defense, the member of the Department of Dissertation Board Support, has all the copies. And before I give the floor to our applicant for the degree, I would like to ask you a question, distinguished members of the board. Do you have any general questions to our applicant for the degree? Is there need to consider the whole list of documents submitted by Mr. Dolgopolik? What's your opinion on that? No questions? Okay. Then, Maxim, please, you have the floor. Thank you so much. So let me present a report on my thesis, titled Constructive Non-Smooth Analysis and its Applications to Optimization, Calculus of Variations, and Control Theory. The thesis consists of 5 chapters, and the report will be divided into 5 parts as well. So the first chapter is dedicated to the development of the set of constructive non-smooth analysis in infinite dimensional case. First of all, we consider the problems of optimization of convex functions, and we introduce global codifferential as a notion. We know it quite well that any convex function can be represented as an envelope of some family of affine functions that we'll call affine support set. If we have function f set, then using affine support sets G and H, we can define global codifferential of function f using formulas 1 and 2. The first set is called hyperdifferential of function f, and the second one hyperdifferential of the f function. And using the global codifferential, we can see the transformation of f function in this formula that allows us to give optimality conditions in codifferentials. So this theorem becomes true. Sufficient condition for the global minimum of the f function is non-negative first components of vectors with a minimum norm from appropriate sets. And if this condition is not met, then we can find a place with the least possible value of f. And the thesis also considered the conditions of global optimality for problems of optimization of the difference of convex functions with constraints, and we won't give them here to be brief. And when we use global codifferentials, we have difficulties associated with the calculus, and therefore we should shift from the presentation of the difference of these functions to global approximations of non-smooth functions. And thus we introduce the following definition. Function f is called codifferentiated in point x if its transformations if this point can be approximated up until the accuracy of the first order using the difference of convex functions c and c. And instead of using global codifferential of this difference of convex functions, the transformation of f function can be given as 6 where maximum and minimum are taken according to what's given on the slide. And these sets are called as codifferential of function f. The first part is codifferential, and the second one is hyperdifferential. And the main difference of codifferentials from most frequently used subdifferentials is the continuity of Hausdorff metric for a broad set of non-smooth functions. And the thesis gives us calculus of such functions defined on Banach spaces, and also we have assessments of remainder epsilon f that allows us to judge how well codifferential approximates the studied function. To be brief, let us give just one of such results. If f is maximum of the end value of codifferentiated functions, then this function is continuously codifferential, and its codifferential can be calculated using theorem 3. And the assessment of remainder is also fair. An important rule in studying codifferential functions is given to quasi-differential, and function f is called quasi-differential if it is differentiated on directions, and its derivative on directions can be represented as a difference of sublinear functions. An appropriate pair of sets is called quasi-differential of f function, and the first is called subdifferential, and the second one is superdifferential. And we know that there is connection between the classes of codifferentiated and quasi-differentiated functions in the considered point. These classes combine, and the following formulas are fair that connect quasi with codifferentials. And codifferentials and quasi-differentials are defined like that. And we also use theorem on average, using which we prove that codifferentiated function with a constrained codifferential are Lipschitz, and continuously differentiated functions are locally Lipschitz. And in the thesis, the set of quasi-differential calculations is used to study the metric regularity of the parametric systems of equalities and inequalities number 8. P is a parameter here, and F is a nonlinear operator. And in order to study this problem, we introduce the following scalar quasi-differentiality notion, just in case we have nonlinear operators. And in order to formulate the conditions of metric regulation, we have the following condition of Mangasar and Fromovitz in terms of quasi-differentials that summarizes the well-known condition of regularity from nonlinear programming. And this condition is formulated in terms of quasi-differential sum of constraints. And the thesis also proved that when we have certain technical provisions, the condition of regularity of Mangasar and Fromovitz in terms of quasi-differentials guarantees the assessment of distances up and metric regularity of the appropriate FP. P. However, the condition of regularity here is restricted, and it's not fulfilled for the following function at the start of coordinates, regardless of the fact that this function is metric regular in this point. Therefore, the thesis considered yet another problem to calculate contingent cone for M set by the nth figure for equalities and inequalities. And I offered the following condition of regularity, 11 and 12, formulated in terms of separate elements of differentials of constraint. And when this condition is met, it is possible to calculate convex subcone of according to formula 13. And it should be mentioned that these conditions, dependent on certain elements of quasi-differential, in Nonsmooth analysis were not previously considered. And these conditions of regularity of constraints were used to draw the following conditions for optimality for non-smooth problems of mathematical programming, number 14. And let us consider one of the results. If x slash is a point of local minimum and it meets the regularity condition of Mangasar and Fromovitz in terms of quasi-differentials, then we'll find a Lagrangian multiplier that meets the conditions in formula 15. And we have an invariant here, regardless of all the constraints. And thesis also gives an example of a simple problem of linear programming, number 16. And here we demonstrated the prevalence and the advantage of extremum conditions in terms of quasi-differentials compared to the well-known conditions of extremum in terms of different subdifferentials. And finally, in the first chapter, we considered the summarization of codifferentiated functions theory on a more general case based on the idea of abstract convex analysis. And let us recollect that recall that phi function is called abstract convex to H if some H functions, if it can be represented as upper envelope of some family of H functions. And abstract convex functions are defined like that, and as well as concave functions. And we also see the gain that can be approximated as a difference of H convex and concave functions. If as H we choose the set of affine functions, then we have this notion of codifferentiation. And if we choose the set of linear functions, then we have quasi-differentiation, and so on. And the thesis demonstrated how theory of abstract codifferentiated functions allows to unify a lot of results of constructive non-smooth analysis into a unified theory. The major results of Chapter 1 are published in the following works. The second chapter is dedicated to non-smooth problems of variation calculus, and in this chapter we consider non-smooth integral functional defined in Sobolev space. In order to study it, we introduce the so-called condition of codifferentiation. And this condition means that under integral f function and its codifferential meets Caratadori condition and growth condition. And to be brief, I give them for finite p. And using these conditions, we've proven the codifferentiation of E and calculated the formula to calculate the codifferential given in Theorem 8. And using this theorem, we obtained conditions of extremum for non-smooth problem of number 18. And we obtained the so-called Euler-Lagrange inclusions in terms of codifferentials, similar to the ones in non-smooth analysis of optimality for non-smooth problems of variation calculus. And we gave an example here, a non-optimal point with asterisk. We have conditions of optimality in terms of subdifferential Clark and K subdifferential, and you see what happens here. And also the thesis gives the optimality conditions for non-smooth balls problem with additional constraints on the borders, and extreme conditions for non-smooth problem with isoperimetric constraints, and we give appropriate examples that demonstrate the efficiency of optimality condition in terms of codifferential compared to terms of subdifferentials. And the major results of Chapter 2 are published here in these works. Third chapter is dedicated to the codifferential descent method. And let us recall the conditions in Theorem 10. The point that meets these conditions is called inf-stationary, and Vladimir Demyanov offered a method of finding inf-stationary points, codifferential descent method, namely. And at every step of this method, we need to calculate truncated hyperdifferential and find, for each element of this set, we need to resolve problems and find element with a minimal norm. However, in practice, this problem cannot be resolved because truncated differentials here are polynomials, are polytopes, and they consist of infinite number of nodes. Therefore, I offered yet another definition here for truncated codifferential, and we need to include just one node here. And I also offer the following modification of codifferential descent, more applicable for practical implementation. At every step of this method, we need to calculate truncated codifferential. Then for every element, we need to calculate from hyperdifferential, we need to calculate an element with a minimal norm of the appropriate set, then conduct linear search along the found directions, and among the found points, we need to find the one with a minimum value of the function. And if some provisions are true, it was proven that all the marginal points and regularities constructed using codifferential descent methods are inf-stationary. And also, I've proven the convergence to zero of instantiarity. That is not characteristic for methods of non-smooth optimization, because in non-smooth case, the distance from zero to subdifferential is not approaching zero. And above all, we consider the behavior of method using convex functions. And method is simplified here significantly, and instead of a linear search, we can use a major step choice. And when some non-constrained provisions are true, we see that convergence looks like that. And that is similar to classical gradient method. And also we consider the behavior of this method on piecewise affine functions. We know that any piecewise affine function can be given as a difference of polyhedral functions according to theorem 14. And using this definition, we can define global codifferential of the piecewise affine function like that. It represents a pair of convex polytopes. Using global optimality conditions for problems of optimization of convex functions, we offer the following modification for the codifferential descent in order to work with piecewise affine functions. And the main difference here is that the first component, a vector with a minimal norm, is not eliminated, but depending on its sign, we can either reduce hyperdifferential or calculate the step. And the thesis also proved that this method converges to the point of global minimum of non-convex affine function at a finite number of steps. And the major results of this chapter are published here in these works. The fourth chapter is dedicated to the theory of penalized functions and modified Lagrangian and augmented Lagrangians. We have a general theory for optimization problems with constraints. And for the unity, you see non-functional form of constraints. And we offer to consider an arbitrary function f depending on lambda parameter, that is usually a Lagrangian, and penalized parameter c. An important role here is given to the global exactness. And it means that for all values of parameter higher than a threshold, the points of global minimum in the initial problem coincide with points of global minimum in problems of minimization of the separating function. And the thesis devised general sufficient conditions for global exactness of separated f functions. And in order to formulate them, we need a local exactness notion given here in definition 10, and also the definition of separating function of penalized type. And it means essentially that in the rise of penalized parameter, the points of global minimum should be associated with points of global minimum in the initial problem. And we've proven the following result: the principle of localization. When certain technical provisions are true, the separating function f from x lambda c is globally exact when the following provisions are true. Essentially, this theorem means that global exactness of penalized functions and modified Lagrangians are defined by the behavior of these functions in small proximity of global minimum of the studied problem. And this principle looks quite simple for linear penalized functions, and it's given here in theorem 17. Though in practice we also see the need to use penalized functions and modified Lagrangians for infinite dimensional problems like optimal control problems, and the principle of localization here is not fair. Therefore, in the thesis, we considered penalized functions for optimization problems for metric spaces, and we obtained the following result when these provisions are true: if the target function meets a Lipschitz condition at appropriate set, and if a known local condition is met, not only the optimal values and points of global minimum of initial problem and penalized problem combined, but also local minimum points and even stationary points as well. And in thesis, I consider the application of this theorem regarding the problems of control of linear evolutionary equations with a fixed right endpoint. And we offer to use penalized functions to take away the constraint at the right end. Therefore, we will include it into the target function in the following way. The thesis has proven that if finite state of xt belongs to the relative interior of the set of accessibility, then the penalized function is rather accurate. It means that initial problem with fixed endpoint is equivalent to the appropriate problem with free endpoint, that's number 24, for all values of C. Major results of this chapter were published in the following works. And the last chapter of the thesis is dedicated to the application of the apparatus of non-smooth analysis to the problems. And here we consider the spread of speed gradient proposed by Professor Peterhof to non-smooth cases. Namely, we let's think that the object of control is set like that, and we also have some non-negative target function q from xt. And our goal is as follows. Define the algorithm of control so that the asymptotic minimization of the target function would be met. And let us presume that the target function differentiated according to directions is Lipschitz. And we have a mega function that meets the following inequality. Essentially, this inequality means that omega is an upper approximation of Pshenichny due to the considered specificity of considered system. And using this function, we can define non-smooth algorithm of gradient, that's formula 28, a non-smooth algorithm of speed gradient in the finite form, and non-smooth algorithm of speed pseudo-gradient. And the thesis demonstrated that when the standard provisions are true, we can guarantee the accessibility of the control problem. And as an example, let me give you the stabilization problem of bracket integrator. We know it quite well that this problem is impossible to be resolved without the feedback, therefore smooth algorithms are not applicable here. In order to resolve this problem, let us consider the target function 30, that is a control function of Lyapunov for bracket integrator. Using non-smooth speed gradient algorithm, we constructed the algorithm to control algorithm number 31. And we've proven that if the initial point is not on axis x3, then this algorithm of control resolves the problem. However, more surprising was the fact that this algorithm of control is continuous along the trajectory of the considered system, and such algorithms were not previously published in the literature. And on this slide you see the results of numerical modeling. That's the trajectory of the system, and that is the control graphs. That's the control graph. And above algorithms of speed gradient, in non-smooth case, the fifth chapter also considers energy control by distributed systems. We have a problem to control energy for semilinear equation of Klein-Gordon, and control acts on the right part of the considered interval, and the measurement can be done for the energy of the system and derivative in the right end. And we have a problem to achieve the set level of energy. And using Q from Z, we get the following speed gradient algorithm. The thesis proved that when performing these conditions on nonlinearity in the considered equation, this algorithm allows to achieve the control goal. And if this algorithm is not smooth, then any non-zero level can be accessed at finite time. And on this slide you see the results of numerical modeling for the smooth algorithm, for non-smooth one, and also for a case when initial level of energy is smaller than the finite one. Smooth and non-smooth algorithm. And finally, we consider the problem when we can measure just the right part of the considered interval. And we offer to use the following observers. And when these conditions are met for the parameters of system, and observe again, we've proven the area of observation. And using this result, we managed to prove the following theorems. If the control rule will replace the energy of system for the assessment by observer, in some provisions, the control function of control goal is met. So that's the graph of observation mistake, and the punctured line is the assessment of the system. And the major results of Chapter 5 are published here in these works. Thank you so much. Thank you. Distinguished members of the board, any questions on the presentation that reflected on the major ideas of the thesis? So, no. Well, may I? Well, I believe we will discuss it later during the discussion. Yes, not now. Okay, no questions right now. But may I? Maxim, when you considered linear evolutionary equation, you used term permitted term of control. Is it a linear operator, continuous linear operator? No, we need certain conditions so that this decision would be used in Cauchy formula, because there is the existence of certain intervals that should be in place. And is it active on the value of control at this period of time, or on the entire control function? On the value at a current state of time. Okay, so that's not mandatory. That's not just continuous nonlinear operator. This can be something general, or that's the operator with some specialized characteristics. Yes, this can be a general or general option as well. Okay, I got it. Thank you. Thank you. Other questions? Okay, let us shift to the reviews. And as all the reviews were already published on the website of St. Petersburg State University, in order to allow everyone to get acquainted with them, I offer just to give the basic provisions, the criticisms or maybe questions to the applicant for the degree. Any objections about that? None. Okay. We had no external reviews for the thesis. Now I'd like to remind you that you can answer the questions after every review, or maybe you can answer all the questions after all the reviews. And I offer to answer all the questions after every review. Any objections about that? None. Okay. So let us shift to the reviews. Vera Alexeyevna, please, you have the floor. Yes, hello once again. I thought I would be the last one. Well, basically, the thesis is very interesting. It's written quite well. I won't repeat my review as it was already published, so everyone could read it. Maksim is a well-known person in Nonsmooth analysis. He's famous for his results, and it was well anticipated that the thesis will be interesting. I have just one question, but I wanted to solicit your opinion on Newton problem. If non-symmetric Newton problem minimizes a resistance of convex object with round base to the flow of vertical particles, it would be interesting to learn whether we can get certain progress or using a numerical method, using new notions and methods that you devised in your thesis. So please, Maksim. Using the methods represented in the thesis, I believe it's not possible to do that, but basically this problem can be represented as an optimization of difference of convex functions on convex set, and we, I believe, can choose appropriate methods to resolve the problem. Vera, are you satisfied with the answer? Nothing more specific here. So yeah, nothing more specific, because in this problem the constraints are quite serious, and the convexity of this function, and it's hard to deal with it. Okay, thank you. So that's your review. Yes? Yes? Okay, thank you, Vera. Now I would like to give the floor to Vladimir Yerokhin. Distinguished colleagues. There is no sound in the book. Could you add up some... So, thank you so much for the invitation. As we have very limited time, and that's quite a complex work, I wanted to concentrate on a kind of broader view on this work. And basically, I would give some comments afterwards. What I want to say that, first of all, the applicant for the degree had very limited time, and we all saw that he was concentrated on the detailed results. He was as detailed as possible, giving us very accurate things, and we should not get lost in these delicacies, but we should assess the work overall. And when you assess the work overall, there are such classical elements as role and place of this work in the system of academic research. So the studies that are ongoing in contemporary mathematics, that's the first. The second point, I believe, it's something that we should do. We should consider whether topics of non-smooth analysis is covered or not, because there are doctoral theses that give rise to publications, to PhD defenses, and there are defenses that just close the topic and that's it, by a monography. And these problems become finished as, classical mechanics or other classical disciplines. So that's important to think about it. And partially, this can give rise to discussions, but I would like to voice it today. And it would be interesting to discuss the difficulties, not in this thesis, but in constructive non-smooth analysis. And if we try to somehow think about it in this way, and I just wanted to mention yet another thing, I'm ready to work in a team with top-notch professionals, and our members of the board are indeed professional, but individually I would not assess this work because my favorite problems are smooth, convex, finite dimensional problems. And here we're talking about non-smooth, convex, and infinite dimensional problems. Therefore, and about numerical methods as well. That's why some aspects of the thesis can be assessed just taking a different look on the issue. For example, chapter 1. Here we're talking about non-smooth problems, both convex and non-convex, and we all understand it well. What a huge gap is there, and that's certainly a topic of Alexander Vladimirovich. But I would say that for engineers, for people who are working with smooth optimization, these non-convex problems, they not just horrify them, but they just inspire awe if you manage to do something with these problems. Therefore, it was quite fascinating to listen to other experts assessing the works. Well, anyway, quite serious and interesting results were obtained by the author, and also the entire work in chapter 1 is aimed at the transfer from some abstract constructions, beautiful abstract constructions, to the resolution of existing problems. And in this regard, I believe we could call this thesis a constructive non-smooth analysis and optimization. But that's the idea of work. And the title, I believe, corresponds to the general idea, and you know, the topic resembles the workshop that was organized long ago. And basically, in chapter 2, we're dealing with infinite dimensional problems. And I would like to emphasize the role of the academic consultant. And for some period of time I observed the work of Maksim, and it should be mentioned that in finite dimensional problems, I remember Mr. Demyanov, the first consultant of Maksim, and maybe the works by Professor Molozyomov were used as well. So basically, Maksim gathered a lot in his doctoral thesis, and certainly there were some predecessors, there were strong works before, so he certainly could not cover that all in his brief presentation. And I liked the following result most. I'll read the part of academic novelty, that's Article 3. You specified in theoretically substantiated, algorithmically implemented calculation scheme of the method of coefficient differential descent and auxiliary a problem of single-dimensional minimization of non-smooth function on beam was replaced by the problem of single-dimensional minimization of non-smooth function on a plot. And it's of interest to experts. And I had contacted Maksim, and he explained that that's a kind of folklore in this field. And people understood that, in fact, you can work on the plot. But there were no specific proofs, and the proof was quite untrivial. So there are different problems. Can you imagine? Well, okay. I believe we understand the difference between the plot and the beam. And the speed of convergence results were quite fascinating as well. That was known for non-smooth convex functions. So that was speed, and the convergence was quite slow. And that was the best option that we used to have. And I believe we could have mentioned the Nesterov monography here dedicated to convex problems, where he considered, where he gave a review. And in this review, he considers this result. But we know that for smooth convex function problems, we can use the Newton method. And Nesterov did it. And we get a cubic speed as a result. But Maksim managed to obtain 1 divided by m. It's better than 1 divided by root from m. But here I'd like to ask a question. Is it the closure of the topic and we need to shift from method of non-smooth analysis to other methods? Or can we just cope with this 1 divided by m? So that's an additional question. Let's think that it was asked during the discussion. And overall, the characteristic of work is as follows. That's a very decent work. Do I need to read out the criticisms that I had? Basically, they were published on the website, so yes, sure, I won't read them out. But Maksim, I believe, will answer them. And basically, that's it. I like the work a lot. I will support it. And I hope that Maksim will answer my questions. Maksim, yes, you can answer. First of all, I would like to thank you for the review and the valuable comments. As for the first comment, numerical experiments on the use of this method are conducted right now by me and my colleagues, and we have interesting results, but right now they were not published, therefore they were not included into the thesis. The second question about numerical methods for problems with constraints, non-convex constraints. That's really a fascinating topic of study, and I plan to deal with it in the near future, but right now it was not included. And finally, as for the third remark, the methods of fine-tuning the penalized parameter, I fully agree with this remark. I should have given more time to that in my thesis, and the fine-tuning methods of penalized parameter, and certainly I should have given a review of appropriate literature sources. And as for the additional question, there's a huge field of study here. I believe, in particular, in convex case, that this method can be speeded up and achieve 1 divided by n squared, but I'm working on that, but this result was not published yet. Thank you. Thank you, I'm satisfied with the answer. Alexei, please, you have the floor. Thank you. Thank you, Ludmila, for the opportunity to deliver my review. And I believe I'm quite a critical opponent because I had 13 comments, and Maksim will have to answer them. And I wanted to add up 2 additional questions, therefore I'll speak on the essence, but shortly, as we need to discuss it afterwards. So the first thing is that, to my mind, that's a very fascinating field, and the thesis as well. And I always like this field due to a beautiful combination. It's practical application and the use of in-depth mathematical theory. Some abstract mathematical facts, like Robin-Mahan theorem or Lebesgue theorem, they are used logically, and they give us a beautiful theory. This thesis can fully be described like that as well. And indeed, here we used quite refined mathematical facts, including the facts of functional analysis, and it's really close to me. And I've used to work with abstract theory of optimal control before. And regardless of this abstract idea, the final motivation here is quite practical. When we see infinite dimensional spaces, the next step we see the optimal control, variation, problems, and I believe that's quite a decent field. And as for this work, here we see the development of constructive non-smooth analysis. The work is based on the foundation established by Professor Demyanov, and that is an additional topic that we need to consider. That's our St. Petersburg University School, and I believe we appreciate it, the representatives of St. Petersburg State University. And therefore here I have an additional question that was not listed among the 13 comments. Maksim, based on the foundation of constructive non-smooth analysis established by Vladimir Fedorovich, and from your point of view, in your original contributions to this theory, can you define something that is key, of paramount importance here, that defines the originality of your approach? Or maybe, in other words, you have a kind of problem front. Can you define a key point where you made a breakthrough and then you developed this platform where you resolve the major attack problem, so to say? What is the situation, or is the situation different? It is more or less even fresher when you worked on several items at a time. So it would be very interesting to listen to your answer. Do you have any key item in this agenda that can be associated with your thesis and with your achievements? Yes. Yes, and I'll have the second question and the 13, those that are in the review, but some of them are just criticisms. And the second question is a technical one, dealing with your basic theorem 432 on linear evolutionary equations, where you take away the constraint on the right hand. I was interested in a condition there. The state that we need to access should lie in the interior of accessibility. Could you please give some examples from equations of private derivatives, maybe classes of such equations where this provision is vital, or you were aimed to add other equations there? And those 13 comments from my review. So I'll be happy to listen to your answers. Maksim, do you have these answers to the questions from the review? Okay, thank you so much, but I'll first answer the questions. This thesis was mostly a kind of general front, an attack on several problems at once, and if I were to give a general result, I would say that it's chapter 2 and theorem on co-differentiability of the integral functional and appropriate optimality conditions, because in constructive non-smooth analysis we haven't seen such previous results, therefore I had to invent new ideas and new techniques to prove the theorems. And as for the second question, first and foremost, the goal was to consider the equation as a wave equation or thermal conductivity equation with control active on the right hand. But in this case, this condition of belonging to a finite state compared to relative interior is hard to explain and, feel somehow. But in my works, I give examples of finite dimensional systems that demonstrate that for two-dimensional systems, if the state is not in the relative interior of accessibility, then the penalized function will not be accurate. And so that's a well-known effect, because in this case, a lot of things are said here when the final state does not belong to relative interior. And as for wave equations, maybe they give us some hope here. For thermal conductivity, yes, I agree with that. Well, frankly, I can't answer this question straight away. Yes, okay, thank you, Maksim. It seems to me that for hyperbolic equations, that's quite real. At least if control is distributed across the area. Okay, now answers to the remarks. First of all, I thank you for all the remarks. And I agree with each of them. As for the first remark, I agree with it. In each of the chapters of the thesis, I should have additionally described the expediency and the importance of the results by applied arguments, as with bracket integrator. I didn't give such example. I lack such examples in the first chapters. And do you have them? Yes, I do, but unfortunately I did not include them in the work, trying to, make it a bit concise. The second remark, yes, I also fully agree with it, that these references to results that are proven in the following chapters should be avoided, or I should have given a kind of explanation. Okay. Then the third criticism. This wording is really not quite successful, and I meant that in case of when the space is reflexive, we need to check the closed character of sets not in strong but not in weak topology. But unfortunately, I misformulated this phrase, therefore you could have understood it incorrectly. I agree with the fourth comment fully. I have nothing to add to that. And as for the fifth remark, I also agree with it that this wording is also not that good, and I should have formulated it otherwise. The sixth remark, I also agree with that, and I should have added it as a comment, because this condition in parentheses is not quite obvious, and I should have explained it additionally. Maksim, maybe you'll do it right now, shortly. What's the point there? The thing is that if the norm is differentiated according to Gödel, then the set here is a convex compact, and if it's not differentiated by Gödel, then it will be a unification of a family of contacts. Therefore, we need additional provision here. Okay, thank you. Then the seventh, Article 7, I want to beg your pardon for the inconvenient definitions, and I should have coordinated this. I should have coordinated this across the chapters. and use different definitions. Then comment 8, I also agree with it. I should have given explanation of the need and role of this condition. Then comment 9. This assumption was given as an explanation. It is true, but it's not proven trivially, therefore I should have given a reference to the source, the monography that gave the proof of this result. I believe there are other conditions hidden in this area that you consider. Indeed, that's, a side comment, so thank you. Okay, now comment 10. Yes, I also fully agree that this term division is not quite successful here. It's not coordinated with the split notion in mathematics, and I use it because it is quite standard in literature on part-wise affine functions, on piecewise affine functions. The remark 11, I agree with it as well. And I should have given examples to illustrate nonlinear problem for 10, or at least give the sources that have such examples. And could you please shortly dwell upon that right now? Maybe you could describe, you consider inequalities on symmetric matrix. What problems did you plan to resolve? In what field? For example, there is a problem to calculate the construction of maximum strength. Something like ordinary bridges with complex metallic framework. And here you can apply this restriction, be it hardness restriction, and you can maximize the load. Here this matrix inequality will be kind of something associated with tension tensor. Yes. Then comment 12. I also agree with it. The results of chapter 5 allow to use it in the general case, to use them in the general case, and if we use a different notion then for bracket integrator, we could leave this case when we have initial point at x3. And in these works given on the slide, in work 4, I use a more general case to be considered the decision on Filippov, but in the thesis, just to be brief, I did not give it. Okay, thank you. And finally, comment 13. Yes, I beg your pardon for this misprints in my work. I should have read it and checked it more carefully before I submitted it for publication. Thank you so much, Maksim. After such a talk, I believe I should draw a conclusion that these criticisms are not key, and they are just side comments, and I had a lot of points for discussion in this thesis, and maybe partially I could have seen it as a shorter one, but expanding the spectrum of the questions for discussion, the author creates more places to make a misprint. Yet overall, the majority of these comments do not influence the overall very high appraisal of this thesis. And I should mention that I'm satisfied with the answers Maksim gave me. Okay, thank you, Alexei. So, Professor Balashov, please. Yes, do you hear me? We do. Yes, colleagues, first of all, I would like to say a few words. First of all, I'm really glad that we have such a thesis because before we had defenses on a combination of works. And I believe this thesis could be defended without any counsel. But as all universities have their own requirements today, so let's follow them. I'm also really glad that this activity, it's very important because in the topic of optimal control emerged in Russia long ago, and it turned out that people left, worked with the topic, and we had just and those experts who offered optimization results, they're quite scarce, and it's wonderful that we have a kind of substitute to those people who left. Now, as for my review, overall, I really liked the work. It is a theoretical work, and we don't need to require proofs, I believe, in this case, though I'm sure that Maksim is able to prove anything, and as that's an analysis work, we need to look at the mathematical essence and in the mathematical context, not in the context of application, and that's an important fact. And in this context, we have a very strong result, and in combination, these results give us a strong mathematical discovery, so to say. And I believe I'll read my comments, and after that comment, what I would like to see, I would read out my description about the field that the work is dedicated to, because it was already described. So my remarks are as follows. The work is a bit excessive, but that's a point that you can judge differently. If you take away all this proofs, someone may misunderstand, someone may question whether it's so or not. And still, this work is easy to read. There are some misprints, but I didn't mention them. But there are really limited misprints, so I don't need to state it as a claim. Here in my second criticism, the example 127 is pretty good. I discussed it with colleagues who are expert in this field on theory of regularity and so on. And I asked whether it's possible to resolve it, and they said there are such theorems using which you can prove this theorem, and Maksim found the value of parameter here. So we have individual results that were provided by Maksim, and the results of problems that could not be resolved by other experts in the field. And these results work. And we've already mentioned the speed of convergence, and we need to prove the linear speed of convergence here. So we need to prove the linear speed of convergence. And as Maksim has already mentioned that he has such plans, I believe it will be implemented later on. And yet another comment that the applicant in this case uses such standard things, and he characterizes the situation in infinite dimensional condition, and here he needs to work with approximation experts. Maybe they'll work on Banach space characteristics. Maybe some of them can be used, in his work. And I believe that's a broad field for further work. And summing up, I would say that this work is a brilliant one, and I'm really happy that I'm really happy that we have such an outstanding mathematician. So thank you so much. So Maxim, you had some criticisms in your review. Yes, I've mentioned them. Yes, there's no need for the answer here because, you know, Maxim just needs to say something and he can do that. Yes, thank you so much for your review and thank you so much for the valuable remarks. I fully agree with them. As for the first remark, I agree that the proofs of assumptions should have been omitted. As for the second comment, I agree with it as well. The thesis lacks summarizing examples, and I'm working on that. And I believe I'll correct that in my further studies. And as for the third criticism, for the third remark, linear convergence speed can be proven when performing sharpness condition, and I hope to publish this result in the near future. And finally, the fourth criticism, the fourth comment, in constructive non-smooth analysis, we do really have certain results on even smoothness, on even convexity of spaces. So that's a fascinating topic for discussion, and I'll bear that in mind in my future work. Okay, Maxim, are you satisfied with the answer? Yes? Yes, I am. Completely. Okay, thank you. Now, Alexander, I give the floor to you. Okay. Not to take too much time, I would like to first of all mention the following thing. Maxim will choose himself a comment to answer, because I've known his work for many years and I worked with them before the publications, and we had numerous contacts at conferences. Therefore, I wanted to focus on Maxim personally. He is a very inspirational person, and he has a very good mathematical skills, well trained by the Leningrad Mathematics School. And for me personally, I would like to draw attention to his turn. This was a kind of unexpected thing for me, and I believe that this turn and this happened due to the academic consultant, Alexander Grigorievich. That was a transition from general problem setting to practical problems. And chapter 5, for me, was an indication of the new things that emerged in the development of our applicant, if you read up until chapter 5. And what else? Indeed, the thesis gives an impression of this small bases that were developed in different directions, and here I believe we should focus more on numerical methods to resolve some non-smooth problems. And as for the new methods, they are required here because all the problems that you consider, Maxim, are non-convex ones practically, and these non convexity is caused by different peculiarities of some of these problems. That's the case. And as a result, mostly you have results of that were not sufficient for non-smooth, for non-convex problems. And I would like to focus more on that in the future. And such a result has condition of global optimality for the global co-differential is based on the definition of affine support base. That's a pretty good result. But can we use it and construct this co-differential like that in several cases? That's a question, because you see what the wonderful example that you've given us in chapter 3. You had a theoretical scheme on co-differential descent, and many tried to apply it to problems, non-smooth problems, and this method found its class of problems, piecewise affine functions that gave brilliant convergence, the global convergence. They're these piecewise functions, piecewise affine functions. They are not convex functions as well. I believe that's one of the good examples, good results. And the only chapter that I didn't like, that's chapter 4, where you try to combine two characteristics of augmented Lagrangian and exactness, as Maksim called it. Exact finalization theory. And there's no need to speed up here. You can use them in a divided manner, because Lagrangian sets works well in convex methods. And overall, my impression is pretty good. And I made remarks that I assess as rather technical ones. And Maksim once again offers, well, Maksim, it's enough to answer just any of these comments. I believe it will be interesting to see what he chooses. So, well, you see, Maksim, yes, you mistaken the patronymic. Yes, I beg your pardon for that. Yes, thank you. And you offered to answer just one critical remark. Yes, okay, on choice. Maksim, please. I first of all would like to thank Professor Stricklovsky so much for his review and for his words. I fully agree with his criticisms, and first of all I would like to beg your pardon for these terms and definitions that were not quite successfully chosen for the thesis, and I should have paid more attention to make this work more convenient to read. And I would like to answer the last remark on examples of variation calculus problems. In all examples we used positive homogeneity, and we demonstrated that functionalities are not limited from the lower part and the global minimum is not accessed. Okay. Alexander, are you satisfied with the answer? In this case, I would like to continue the discussion. And how can you consider this problems? Because previously I haven't seen that people offer to consider such problems. What's the point to improve controlling these problems if it's initially clear that it runs away to infinite area. Those were illustrations, and they were artificially developed to demonstrate the difference of co- and subdifferentials terms. And those were the simplest examples that I managed to devise. Okay, I'm satisfied with the answers. Okay, thank you. Professor Stanyakin, please, you have the floor. Fyodor? Yes, thank you. Do you hear me? We do. Yes, we do. Well, I'll try to be brief. Certainly a lot was done. That's a serious work, and we just can support the previous opinions that, you know, by a combination of these works, we could have given the degree to Maksim. What I liked most is chapter 2 on variation functionality and on the conditions, and also on the third algorithm, though the last chapter is quite impressive as well. The one that gives specific numerical modeling. So everything is substantiated, all the positions, and I won't list them all. And there are 3 items that I've given in my review. And as for chapter 2, the optimality conditions, he compared these conditions with other subdifferential conditions. And can you say anything? Because you've demonstrated the advantages, and the question is, what can you say about the drawbacks of this methodology that you studied in your work compared to the classical options, classical approaches? But that's just out of interest, question out of interest. And as for questions 1 and 2, they're mostly dealing with numerical method. And the question, you know, mostly compared, we mentioned a lot about the speed of convergence, and I wrote about it. And what's interesting is to compare the complexity of these operations with the classical methods. So how can you say anything about it? And as for numerical experiments, you've already answered these questions, and it's clear that that's in your plans. And as for the assessment of the speed of convergence, wanted to give a comment here. You quoted Nesterov, for sure, but I believe this assessment is optimal for large dimensionality, because we can use ellipsoids for limited dimensionality to work with the speed. And also it was mentioned the sharpness issue, and I didn't write it in my review, but you mentioned that you wanted to prove 1 by n squared, and there are composite optimization problems, and formally these are not non-smooth problems as well. And also in Nesterov book, we see the description of possibilities, and that's just a wish. If you want to continue the topic, I would recommend to study these sources as well. So that's just a wish. And second wish is to pay attention to different stochastic and randomized procedures for the future, because this would be, I believe, interesting. And overall, the work is quite decent. It has a lot of results, and in combination, I believe they make a good contribution to the field, and we can continue doing a lot in the field, and therefore, I believe we could award the degree of Doctor of Sciences without any questions here. So that's a huge work, and I am sure that this work will have a very good future. Okay, Fyodor, you had comments in your review. There was just one question there, so Maksim. Yeah, I did not mention them. I didn't read them out. Yes, Maksim, you can answer. Thank you so much for your review and for the valuable remarks that you have given me. And if I follow the order, I would say that the main disadvantage of the optimality conditions is the relatively limited conditions. Optimality conditions can't be used for variation calculus with a subintegral function, and many conditions of optimality will be applied here. As for the second remark, I would say that in many cases the methods unfortunately have high labor intensity of iteration than any other methods. There are some particular cases sub-problems can be optimized, and this can give us a rather high efficiency. And I really like comparative analysis, and I'm working on that with my colleagues, but right now these results were not published. And finally, the third remark, I fully agree with it. The comparison of the speed of convergence, a comparison of the assessment of the speed of convergence is not full, and I should have described it in more details, and I should have given more references to the literature sources. Thank you. And finally, that's my turn. I just want to say that I personally liked this beautiful method used to find global minimum of difference of linear affine functions, because we all know that globally we don't have a lot of methods for global optimalities. And I believe that this work, I just read a few words from my review. As currently non-smooth analysis is widely applied, certainly this work is relevant. And the work is dedicated to the development of new methods of constructive non-smooth analysis. And sure enough, it represents a direct theoretical, and it gives direct theoretical and practical interest. And my reviews are mostly, my comments are mostly of editorial character, and some paragraphs are quite concise. You could have described the proofs in more details, but my remarks do not compromise the overall very high value of this work and the results. For in conclusion, I want to say that a thesis by Maksim Dolgopolik titled Constructive Nonsmooth Analysis and its Applications to Optimization Calculus Variations and Control Theory meets the requirements of the order. Number 11181/1 on the procedure of granting academic degrees at St. Petersburg State University. And Maksim Dolgopolik deserves the academic degree of Doctor of Sciences in Physics and Mathematics in specialization 111, Real Complex and Functional Analysis. And Articles 9 and 11 of the above-mentioned order are not violated. So, Maksim, you can answer. Thank you so much for the review, and thank you so much for the comments. I fully agree with them. And I want to beg your pardon for all the misprints and the work for this repeating definitions. And I should have given this information in my thesis. And the last criticism, I fully agree that in paragraph 4, that paragraphs 4.1 and 2 are not written quite well. They are extremely concise. And I should have described theoretical results in more details. And I should have given some examples to illustrate. Thank you so much, distinguished colleagues, dear members of the board. Is everyone satisfied with the answers? I am. Yes, yes. Okay, as we have no colleagues present right now, I would like to give the floor to the consultant. Please, Alexander, you have the floor. Yes, distinguished colleagues, tell us about Maksim and his work. Well, I should say that today, regardless of the harsh situation in the world, I have a happy day. Today, an outstanding member of our lab defends his thesis. And these words that were mentioned about this work by the experts of our board, I believe, just prove it. And I want to say a few words about our applicant for the degree and about our communication. We got acquainted in the year 2014 after he defended his PhD at the university. And he was recommended by Vasily Molozomov to our lab. And he is, a kind of second father who always supported Maksim. Was a kind of godfather for him. And we were so lucky that we just won a Russian Foundation for Basic Research grant, and for 5 years we had no financing problems. This was mere luck, a very lucky combination of events, and it gave us an opportunity to work, and it gave Maksim an opportunity to develop in his field. Because, freedom is very important for creativity in science. And he used his colossal creativity to obtain a range of fascinating results. And the first results were obtained right after, in a month after we discussed it all. He brought me an article that was accepted for the forthcoming European conference, and after that a range of results was obtained, and mostly they are concentrated in chapter 5, maybe not all of them. And there are two fields, speed gradient and control of distributed systems. These are different fields, you know, and Maksim has a surprising talent to deal simultaneously with different things, and it was demonstrated quite well here. And as you see, that's just the 5th chapter. And as for the first 4, he did them himself, studying what he wanted to, developing the results he obtained before. And he is a full-fledged scientist, a person who is searching for new problems, for new methods, and who manages to secure success on his path. And he is a really modest person, surprising enough. You know, I consulted him rather than he consulted me. And that's not a surprise that in 2018 Maksim was awarded the Medal of Young Mathematician of the St. Petersburg Mathematical Society. And that's quite a prestigious award that was given to fields laureates Grigory Perelman and Stanislav Smirnov and other scientists who are well known across the world. And maybe for the first time, a person working in applied mathematics became a laureate of this prestigious award. And I believe that finishing up his defense, he will have an additional field for discoveries, and I believe he'll have more achievements. And he is a person of such an academic skill that we don't have a lot of such people in our country, and I really wish that he continued to work and obtain his results here in Russia. And I would like to wish him even more important awards in the future. Thank you. Thank you. So, distinguished colleagues, does anyone else want to say anything? Yes, I wanted to add up, indeed, that the results are of such a good quality, and you know, we don't have these results are scarce not just in Russia but across the globe. Okay, thank you, Vera. So here we stop the discussion and we stop taking questions. And before we draw conclusions, and before the final vote, I would like to ask all the members of the board, and I would like to ask our applicant for the degree, do you have any questions on the procedure of our defense? No. Okay, then the vote. Distinguished colleagues, before the vote, we have an opportunity to announce a technical break to discuss the results of the defense. And this discussion will not be broadcast. How do you think? Do we need such a close discussion? So, to my mind, we don't need that. Well, if anyone wishes that, we may. Yes, anyone can ask for it. So I believe we've talked a lot about the case already. So in this case, we need to check whether we all hear and see each other. I believe yes. Therefore, I raise a question on the award of the academic degree of Doctor of Sciences in Physics and Mathematics and Specialization Real Complex and Functional Analysis to Maksim Dolgopolik. And I would like to emphasize that voting for the award of the academic degree, each member of the board agrees that Article 11 of the order is not violated by the candidate, and let me quote it. In the thesis, the applicant for the degree is obliged to cite the author and or the source of materials or individual results borrowed. Using the results obtained by the applicant personally or in co-authorship, the applicant for the degree is obliged to note this circumstance in the thesis. And I would like to remind you that the decision of the board is valid, providing more than half of the board members voted in favor, but not fewer than 3 people. That's in conformity with Section 17 of the Order on the Procedure of Granting Academic Degrees at St. Petersburg State University. So, Professor Yerokhin, what's your opinion? I believe that Maksim Dolgopolik deserves the academic degree of Doctor of Sciences in Physics and Mathematics. Okay, you vote for the award of the academic degree. I do. Next, Professor Matveyev. What's your opinion? Yes, I also vote for the award of the academic degree. Professor Balashov. I also vote for the award of the academic degree. Professor Strikalovsky. I also vote for the award of the academic degree. Professor Stanyakin, what's your opinion? I also support this work. And Professor Roshina, what's your opinion? Yes, I also vote for the award of the degree. Okay. And I, chair of the board, Professor Polikova, vote for the award of the academic degree. Thus, distinguished colleagues and guests, I would like to announce that out of 7 members of the board, all 7 voted for the award of the academic degree, no one voted against it, and no one abstained from the vote. Thus, we make a decision to award the degree of Doctor of Sciences in Physics and Mathematics and Specialization 111, Real Complex and Functional Analysis, to Maksim Vladimirovich Dolgopolik. And now I would like to give the floor to Maksim for the finalizing remarks. Thank you. First of all, I would like to thank my first thesis supervisor, Vladimir Demyanov, and I would like to dedicate my work to his memory because my results, the results of the first 4 chapters, were mostly the continuation of his work, and I tried to finish up what he started. And unfortunately, he did not manage to finish it. And I would like to thank Vasily Malazyomov for his help and support during all these years, for his help in employing me, for his attention to my work, for his consultations. So I would like to thank him for that as well. And I would like to thank Professor Fradkov as well. Thank you so much for the kind words extended to me, for working with me after my PhD defense, for giving me this freedom of study and research. I'm really grateful to you for that. And finally, I would like to thank each of the members of the board for their attention and for the time they found to read my thesis and to attend this meeting. Thank you so much, everyone. Thank you. I believe we all want to congratulate Maksim on this well-deserved degree. Thank you. And I believe here we stop our session. I would like to thank everyone for participating, and please switch off the broadcast. Thank you, everyone. Goodbye.